So far we have seen the design of a charge pump PLL, and we were focused on designing this PLL for one single output frequency. Now, as we go ahead and we employ this PLL in a given application, it is often required that you may need to change the output frequency. Okay, for the same PLL. So, let us just look at the PLL block diagram which we have been studying in depth. So, a charge pump PLL, this is what you are looking at. We have a PFT followed by charge pump where you get up and down pulses, okay, and then output of the charge pump goes to a loop filter like this, and then you have your capacitors C1 and C2, right, and here you have a VCO, okay, and then you have a divider in between. So, I will write this as N here, and this is your PL. Okay. So, you have a reference clock and you have an, from the VCO you have output clock. Okay. Now, in most of the applications what you will see is that your reference frequency in general remains same, because you are going to use a crystal as a reference. So, this is the symbol of the crystal I am using, crystal, and this feeds into your PLL. Crystal, it can be a piezoelectric crystal or it can be temperature compensated, Kvco voltage compensated. Here you have this ICP and V control. Okay. So, in our case what we have is this crystal which gives us the reference signal here. The frequency of the reference is Fref, and we know this is equal to your output frequency by N, right. What we want is F out to be equal to some M times Fref, where M is variable, and how we make this M as variable, that is something which is for us to decide. Okay. So, in the PLL loop what you see here is that the feedback loop will always enforce that the feedback signal, the feedback signal at the input of the PFT and your reference signal, both these signals will have the same frequency. So, in order to change the output frequency, we can have two possible methods. One, by just changing the, because the feedback loop is going to enforce that. So, I can have a divider here, let us say divide by N1, and or a divider in the feedback which is divide by N2. So, now the reference which goes to your PFT is this, and this is your feedback signal. So, Fref in this new case is equal to your crystal frequency. So, you can say F crystal frequency by N1, and your output frequency or feedback frequency F feedback is your F out by N2. The PLL loop is going to enforce that your reference frequency is equal to your feedback frequency. So, F out is equal to N2 by N1 times F crystal. Okay. So, if you want to change the output frequency, you can change the output frequency in this particular manner. Okay. You look one by one. If I have F out, I will keep one of it is fixed. So, N2 is fixed, for example, and N1 is varying. Okay. In that case, the maximum frequency which I can have in my system, okay, f out max is equal to n2 fixed divided by n1 minimum. Minimum value what you can have. Minimum value of divider is 1. So, you do not divide whatever your crystal frequency you have, you fix n2 times fix that crystal frequency is something which you will get. Okay. Similarly, if I want to keep my n1 as fixed and make my n2 variable, then n2 times n1 fixed times f crystal. So, in this case whatever you have your n2, right, depending on your n2 you will get the output frequency. The problem with having a divider in the crystal path is that f crystal is typically limited. For a good phase noise at the crystal output, the crystal frequency is typically limited. Okay. And if you want a really good high frequency crystal, the size will be large, the power consumption will be more, and your cost will also be high. So, crystal frequency is typically limited. So, dividing the crystal frequency in general is not an option. It is not that technically it is not possible, it is very much possible, but quite often what we use is we vary only the divider part here. Okay. We vary the divider division factor in the feedback path to vary the output frequency. Okay. So, if we do that, let us say you have both the options, but most of the time we use this one only in the feedback. So, given this PLL where you are only varying the input frequency, okay, and this is your feedback. Now, I will just use a divider n here rather than n2 to make sure that you have only one divider in the PLL. So, what are the problems or the challenges which you have when you want to have a large tuning range? So, here for simplicity I will just remove the C2 for now, you can add C2 just to avoid any complicated expressions for now. Okay. So, in this example let us say f out is equal to n times f ref, or in our case f crystal here. Okay. And what I want is I want to have wide range for this crystal, for this output frequency. So, I will just choose one factor that the delta f out which I want is like 2x range. As an example, 2x, when I say 2x range, delta f out is 2x. In general, when we write like this, it is like 2 times delta f, or 2 into, you can say this division factor is varying from n to 2n. That is how you want to have. So, when your division factor was n, so let me just write it here. So, when your division factor is n, okay, when divider is n, in that case f out is equal to n times f ref, okay, and the divide, you are able to change the divider ratio from n to 2n in the PLL, f out becomes 2n times f ref. Okay. So, the range which we cover is 2x. As an example, just to make it look better, so let us say your f ref is 40 megahertz, okay, and n value is something at 16, right. In that case, your f out value is 16 into 4, 64. So, you are 640 megahertz, and I am able to change this value to 32 and the PLL still operates fine. this is equal to your 1280 megahertz. So, this range if you look at it, this is like a 2x range which you have, that is what we call as a 2x range. Okay. So, for this 2x range, if we just change the divider n here, right, what are the problems which we will face? Is there any issue or there is no problem at all? Okay. So, when we want to extend the range of the output range of the PLL, in that case let us write down the loop gain expression of the PLL. Here this is ICP by 2 pi times your R plus 1 over SC1. So, you have R plus 1 over SC1 times Kvco over S into 1 over n. So, here we have seen this multiple times. You have 2 pi S square C1 n times Kvco into 1 plus SR C1. Okay. So, when we design our PLL, we design our PLL in general for the highest frequency which we have, okay, to minimize the jitter at the output. So, that is what we are going to do, and then we did all our noise transfer function analysis and bandwidth and so on. Everything was done perfectly, and in our example for let us say we want to change n from here n which you are seeing, n can be varied from 16 to 32. It is not only like 16 and 32 or 16, 17, 18 or whatever n you have, this is the variable range which you want. Okay. So, if I keep everything else the constant and I vary this particular n, there are many assumptions which we can make to say that okay, our design is a good design here or an optimized design. These assumptions may or may not be valid. Okay. So, first one is at n equal to 32, let us say you did noise analysis, noise versus bandwidth analysis you did, right, and you chose certain noise versus bandwidth analysis gave you ICP R C1, right, for a given phase margin. If you had C2, then you will also get C2. For expression I am not writing C2, but assume it is there. So, you get all these component values and this as omega u as 2 pi times Fu. So, your unity gain frequency is optimized for this case. Okay. Now, suddenly I go ahead and change n to 16. What happens? If I change from n equal to 32 to n equal to 16, my loop gain expression, here it was ICP Kvco 1 plus SRC1, and here it becomes 2 pi S square C1, let us say this is 32, right. It had a certain unity gain frequency, suddenly it changed to 16. Now, for this loop gain expression, if you do not do anything, right, whatever unity gain frequency you had in the previous case, the unity gain frequency in the second case is, you can say, Fu dash is 2 times Fu. Okay. How did we get that? Well, from the loop gain expression, assuming your unity gain frequency is much larger than your 0 frequency. So, you can find that out, that is equal to your ICP Kvco times R whole divided by 2 pi times 32. This is what you had. Now, as soon as I change my n factor, this is the n factor which you get. So, omega u dash has become ICP times Kvco times R divided by 2 pi times 16, which is what? Which is 2 times omega u. So, your unity gain frequency just changed, and if your unity gain frequency changed, then your noise analysis is also going to, or noise at the output, total jitter at the output changes. Okay. Now, previously omega u might be the optimized bandwidth. Okay. Now, omega u dash is not at all an optimized bandwidth. It is just, you can say, a byproduct of whatever you did to change the divider. Okay. So, this is something which may or may not be good for the design. This implies that in order to have an optimized design, bandwidth should be some function of the divider n. Okay. Now, you can say whether it should. So, typically if it is the case that I want to cancel, the oscillator noise is dominant and the maximum bandwidth which we can have is f by 10. So, if you want to keep the bandwidth constant across the output frequency, then you can say I would like to keep the bandwidth directly proportional to n. Okay. So, here a bandwidth is in this case what you are seeing is the bandwidth is some value, here the bandwidth becomes twice. Ideally, I have to do something to this expression such that the bandwidth for this still remains omega u. It should not increase to omega u. Yes, I know that this particular divider value changes. Okay. That is something which you need to fix. So, if you look at the loop gain expression which we had before, so I will just paste the expression here which we had earlier, right. I know that in this loop gain expression my n changes as per the required frequency. If n changes as per the required frequency, I would like to change some other parameter. So, let us say you optimize everything at the highest frequency where you need the minimum jitter, and then you would like to keep the bandwidth fixed, because bandwidth is decided by the reference frequency, the maximum bandwidth you cannot increase it more than a certain value. So, you would like the bandwidth as a function of n, okay, and or let me say the optimized bandwidth from noise versus bandwidth analysis. So, you would like to do that. Either thing is something which you will utilize. Okay. Now, given the PLL, right, when you have this whole block diagram of the PLL or this thing, there are few things which you can't change. You cannot change the gain of the PFT. Okay. Charge pump is you have a charge pump current, that is something which is in your control, right. RNC, changing the capture C is typically hard because capture has a large value and large area, and adding tunability to the capacitor is difficult to implement, okay, and or you can say it has a lot of cost of in terms of area. Resistance is other thing which you would you can try to change. VCO is not that much in your control, but we will see how we can control the KVCO. So, we look at each of these parameters and see whether we can change it or not. So, ICP, KVCO and this parameter. So, there are few parameters which if you change, right, you may not find if few parameters may be easy to change without changing phase margin and other values. It will just help in retaining the unity gain frequency. Few parameters are difficult to change, okay, but there is nothing which stops you to do that, right. So, in this case let us look at it. If I make ICP proportional to n, for example, if such is the case, I can write ICP as n times I naught. Okay. If somehow when I am getting this bias current, I make this ICP proportional to the divider ratio, right, then in my loop gain expression I am going to have, in place of ICP, it is n times I naught times Kvco into 1 plus SR C1 divided by 2 pi S square C1 times n. So, what you see is that your loop gain transfer function is actually independent of n. Your unity gain bandwidth will be retained, okay, and your all your noise transfer functions, they are going to be so noise transfer function depends on loop gain, right. So, only the thing is the charge pump transfer function will vary, but your loop gain will remain constant. Okay. Charge pump noise transfer function has your ICP by 2 pi in the expression other than the loop gain, which will vary. Okay. Other than that, your unity gain bandwidth Fu remains fixed. Okay. There is no change in phase margin. Now, you can ask a question that okay, how am I going to change ICP with respect to n? Well, you know what divider ratio you are going to use. So, based on that you can have a bias current which is switchable, okay, and from that bias current you can change the charge pump current. So, very simple implementation, you can think about it, that you have an external current which is given to a diode, just an example, okay. This is I naught, and if I want to take this current as n times I naught, maybe I can do this. So, I can, this is just one example, do not like okay, this is the only way you can do it. So, you can have switches here, and these switches are going to finally give your bias current to your charge pump. So, if I want this particular thing to be tunable from I naught to whatever n I naught, I can keep this 1 to n times I naught or 2 n times I naught if I want that. Okay. So, based on which how much current you are switching in, this particular current is then mirrored in the charge pump somehow. Okay. The basic charge pump which you would like to use, you can mirror this current in the charge pump. Okay. I am not showing the exact circuit, but that is what you can do. So, in this way you can control your charge pump current. Now, this is one way to deal with this. Okay. Another thing is the Kvco variation. Okay. So, now Kvco normally we do not vary, we do not change the Kvco that much, but if you like, if the design needs, that is also possible. The reason here is that as you change the ICP current, your unity gain bandwidth remains fixed, but because you change your ICP current and you are reducing your ICP current, so the noise from the charge pump current will, overall noise from the charge pump current will increase, and if the overall noise from the charge pump current increase, it may lead to large jitter as compared to what you think. Okay. So, that is something which may go against while changing your ICP with respect to your n factor. Okay. Then you look at varying Kvco. So, the case which you have seen earlier is that to control the oscillator, you had this particular current source, which feeds into your ring oscillator, for example. Okay. So, you have this ring oscillator whose output voltage is something which you are controlling. So, this is your V control and this is your VDD VCO. So, here we know the KVCO is defined as the derivative of F output with respect to V control. If you go and look at the exact curve on F VCO versus your V control, you may find something kind of this curve. Okay. It may or may not be linear depending on the range which you want. So, this may be F lowest frequency, okay, and this may be the highest frequency, F low and F high. You could write it like this. Okay. So, what you would like, so when you are, think about it, when you are changing your frequency from 1280 megahertz, 1.28 gigahertz to 640 megahertz, what happens is this control voltage drops. Because of this drop in the control voltage, this voltage increases, right, and this voltage also drops. That is how oscillator frequency is controlled. So, this device in this whole of your transfer function, what you are looking at is the following. So, I am just writing, let us say, the DC gain of this loop, the closed loop gain is 1. We know that what we are seeing here is from your V control, you change your PMOS gate voltage, which is Vx, Vx changes VDD VO. So, exactly you change the same voltage. Okay. And this particular loop, you have a certain loop gain, and the loop gain is whatever the gain DC gain of the amplifier GMA RA times the gain of this PMOS with the RVCO. So, you can say GMP times RVCO in parallel with RDS. So, this is the DC gain we have seen, and at DC these two control voltages are same. Now, what I want to do is, I know that when the frequency of the oscillator reduces, at the same time the current of the oscillator will also reduce. So, in this particular case, if you want to change the KVCO, what can you do? Okay. By the way, the gain which we are having here, this gain may not be large. Okay. So, there are a couple of ways in which you can do it. You can split this current source. So, earlier the current source which I had, a single current source like this, okay, with this node as Vx and this particular value as VDD VCO. I can change this, maybe just for an example, I can have Vx and the switch. Okay. So, you can have this here. Similarly, you can have multiple of these. So, you connect all of these and this is connected. Okay. So, by doing so, what you are actually doing is you are changing your KVCO. And how will you change your KVCO? Because you will change your this GMP and RDS are the values which you will change based on your current source. Okay. So, that is something which you will do, and based on this your KVCO will be changed. Now, here the difference is that the closed loop gain, if I just look at it, the closed loop gain DC gain VDD VCO divided by V control, that is nothing but loop gain by 1 plus loop gain. So, ideally this is equal to 1, and depending on how much contribution you are having from here, this is going to change the Kvco. Another way will be that if in case you are not using the amplifier and you only have this one directly as V control, connected to V control. So, let me just okay. So, if this node happens to be V control, then you think about it, your VDD VCO here divided by V control is nothing directly equal to whatever the GMP you have of the transistor, GMP times RDS parallel R VCO. R VCO will also change based on the current which you are having in the oscillator. So, this is the gain which you VDD by V control, this is the gain which you have. Now, by switching these current sources, in one case you have all of them off, all of them on, and in the other case you can think let us say few of them are on and other are open. So, this is directly changing your GMP and RDS when RVCO is also changing. Okay. So, in this way also you can actually control the Kvco of the oscillator. All these things you can work out based on your design requirement. Okay. So, then the other thing is which we would like to change is the resistor. Okay. Resistor and capacitor are the two other parameters which you can change. The problem while changing the resistor is, so one thing is the resistor itself is susceptible to process variation. Okay. So, if I vary resistor, okay, omega z also changes. So, your the problem which you will see is that if you vary the resistor, because omega z changes, so your phase margin will also change. So, one way is the unity gain bandwidth is only proportional to R. So, you look at this expression here, right. So, unity gain bandwidth is this. If unity gain bandwidth is only proportional to R, you want to compensate for the unity gain bandwidth, but you would not like to change the 0 location because that is going to compromise your phase margin. Then you can say that okay, given these two expressions, so one is the loop gain which is ICP by 2 pi into 1 plus SR C1 divided by S square C1 times Kvco over N, and your omega u is ICP Kvco times R divided by 2 pi N. Okay. So, let us say if N reduces, I want to reduce my N to keep the unity gain bandwidth constant. If I do that here, right, it is not sufficient, because if I do this reduce R, my 0 frequency changes. So, I have to increase C1. Okay. Now, if you increase C1, you see your loop gain again drops. So, this method of changing the resistor to compensate for the change in N is not that fruitful, because as N reduces, you reduced R. To keep the same 0 frequency, you increase C. So, okay, your bandwidth remains fixed, but what happened is your overall loop gain changes. Okay. So, that is what you will see. So, what we are doing here is the following. Let us just look at. So, in one case we had this particular you have as a square. So, I will just write it like this. Okay. So, when N drops only, what you have is your loop gain. This is the magnitude of loop gain with respect to omega. N drops, your loop gain changes like this, right. So, this is going to do this. So, effectively you can say unity gain frequency changes. So, how did you restore the unity gain frequency? You reduced R. Okay. So, reducing R actually shifts your reducing R. If you just take reducing R, then what it does? It reducing R, your unity gain frequency goes high. There are two changes. One, your omega z changes. Omega z here is 1 over R C1, right. So, I changed my omega z. If I change my omega c, what I am doing is I am just shifting this curve. Okay. So, what I am doing here is I am just shifting the 0 frequency such that this is what I do. Okay. I shifted my 0 frequency such that my unity gain frequency remains same. But what this has done is this has actually changed our unity gain frequency. Okay. So, then if my unity gain frequency has changed, then what I would like to do is I would like to increase my C1 to bring it back, and if I increase my C1 here, what I have done is, so I bring it back and I increase C1 such that my 0 frequency remains same and I still get the unity gain frequency to keep the same phase margin. Okay, that is what I need to do. Well, the curve is not exact, but what we are doing is I hope you got that idea. Okay, let me just remove this. So, by increasing C1, you effectively you can say that my N1 reduces, my C1 increases, and I can but C1 increases, I retain the same curve. Okay. So, this curve is retained by not changing ICP, but by reducing R and increasing C1. The benefit of this is charge pump noise does not increase with increase in N. Okay. But what is the cost? Large capacitor is the problem. Large capacitor cost area on chip. So, what you see here is every trick here is having some trade off associated with it, and these trade offs become this is something for the designer to decide which trade off he or she would like to entertain. Okay. So, this is how we vary the bandwidth, we vary the output frequency or make the PLL analog PLL wide bandwidth. Okay. Thank you.